Now, this is something where if we're running a DBMS, so this the database administrator function, this is where we start to earn our money. So what I want to talk about is a bit of understanding what the issue is, different sorts of organisations, indexes and keys, and so on. And then some rough calculations about how we can estimate performance based on file organisation. Right. So if we remember our basics for storage. Storage says at the top of the heap we have main memory. It's volatile, it's precious, it's a limited size, even though there's much more of it than there ever used to be, but it is still our most precious resource. And then we have various forms of secondary storage, typically disks. These are larger, cheaper, they're non-volatile. Very often for a decent database organisation, putting a bit of flash in helps because you can write, because it's non-volatile, you can write to it and you don't lose your updates if the power goes off. Okay, that's good. And you can write to it rather more quickly than you can write to disk. So typically this is something that you might find around a disk controller. Right, so secondary storage. Now, how is secondary storage organised and how do we transfer between secondary storage and primary storage? So we talk in terms of pages. Right, so for the next hour we are going to be in the world of pages and files rather than tuples, relations and so on. Okay, we've just gone crash, 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 and we're somewhere near the physical level of things. So we have our physical unit of transfer from disk to memory. Obviously the disk got no idea what's going on. It just says, I've been told to fetch something or to write something. I fetch, I write. Whatever it is, it's just stuff. So a disk controller says, right, the disk is divided into chunks, and they're all equal sized chunks, because this makes life a lot easier, moving things around. And these are typically multiples of 4 kilobytes. Okay, we'll see next week that multiple of 4 kilobytes could be 64 megabytes. But that's a different story. It's Nixon's story. And what that means is that you're getting typically several records, several logical records per physical page. Now, okay, so what we're doing with our file organisation is saying, how do we map between our logical records, the things that we deal in, tuples and so on, and stuff that the lower levels of the system deal in, which is disk blocks, pages, right? Now, okay, so then we have access methods, techniques for storing and accessing logical records. So this is all about indexes and so on. Okay, so there's the storage hierarchy just as a picture. And just trying to get your heads in the right place, there is a schematic of a disk. So if you start thinking about this stuff and you look at older material, you'll find that people get excited about disk arms moving and settling and latency and so on. There's a reference at the end from about 1994 or something. But essentially a bunch of guys at HP set about modelling a disk in excessive detail. And they did a lot of different approximations in more and more detail, getting more and more realism in for their model of how disk behaves. And the conclusion was that actually, if you treat a disk as a logical sequence of blocks, so pages, then you can pretty much ignore the rest. Because if you're designing, okay, so what you're doing, right, okay, so here right, you've got stuff there, here you've got the disk spinning round, typically 7,200 RPM, off it goes, and you've got the disk head, and the disk, the disk head sort of moves in and out and in and out, reading. Now obviously if you ask me to read a whole bunch of stuff, then it's got to start from where it is, move to where it needs to go to, settle on that track, wait till the start of the thing that it's looking for comes round, and then read. Okay? Now, if you know you're going to read quite a bit, and you're a reasonably sensible disk designer, then what you do is you organise it so that you know that by the time this thing settles, the bit you want is just going to come round. If you assume that things are written just in order. So that approximation, you can treat a disk as just some large sequence of pages is about right.
When you defragment the disk to get all the blocks in order?
Okay, so what happens on your typical PC disk is you're writing things into files. These get expanded, deleted, what have you. And as they expand, if they come round and find, oh, look, something else started there, then you put a pointer in saying, this is where you've got to go, or you put a pointer in the file table, so this is where you've got to go next. So what then happens is one logical file gets smashed into lots of little fragments, right? So your disk head is going zip, 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 zip all over the place for reading very little. What database management systems usually do is when you install them, essentially they say to the operating system, okay, give me a big lump of disk space. They'll ask for a big lump, and they may well just tell the operating system, as far as you're concerned, I've just got some huge file.
So how does it decide on how big the lump is?
That's an interesting question. And okay, so it'll start. There's some PC implementation of Postgres. You must have. I think it starts with something like 64 meg, and we'll take chunks, extra chunks that you need. If you're doing the sort of big grown-up installation with ZOS and multiple servers, then you've got lots of little tuning knobs. You know, how big do you want it, and you get a dozen parameters out of it, actually. So, yeah, it all depends, is the short answer.
Yeah.
But so as far as we're concerned, our database management system has grabbed a chunk of space and is going to organise it sensibly, and it's not going to let the operating system get in its way if you can help it. Because it says, I know how to do databases, general purpose operating systems, no, you don't know how to do databases because you're doing lots of little text files and bits of images and so on and so on. And I don't know what started making a noise, but it's irritating. Anyway, right, so, disk. Right, so we have our disk. And, right, so there's our disk. And we've got our query processor, our lock manager, our recovery manager, all sorts of things. Now, Beatrice, I think, was talking about transactions, locks, recovering, that sort of stuff last week, yes? Yeah, good. It's all right. So, all those things, whenever they want something, they go and ask the buffer manager, which runs the buffer pool. Right? And the buffer pool contains the most recently accessed pages. So again, when the database management system starts up, it says, okay, I'm grabbing a chunk of memory, this is my buffer pool, and if you look in the bowels of the thing, we'll find this is a tunable parameter as well. So, that buffer pool says, all right, this is where all the pages that have been fetched recently live. So that when any of these guys want a page, you give it to them. If it's not there, you go and fetch it. Okay, so the buffer manager controls the interface between the disks and everybody else. What you hope is that most of the time the page you want has been accessed reasonably recently, in which case it'll be there and you don't have to wait for the I/O to complete. If it's not there, you've got to wait what in computing terms is a long time for that disk to spin round, for the diskette to move to where it wants to be and start reading and so on. So that's what your buffer pool's doing. There we are. There's some words to explain that. Okay. And that locality of reference is common. Right. So that's the basic organisation. Now, we're trying to do stuff. So we have a query. We can look at our query. We know whether it's going to be an exact match query. So we're trying to find customer number 1234. Yeah, and we know there's only one customer 1234, so we know that it's an exact match for one record. It might be that we want all the customers called Smith, in which case, if we've organised it right, which we'll come to later, then we can find the first Smith, and we keep on reading until we've got them all. Right? Assuming that our file is organised in the right way. If we want all customers based in London, and we've not got any indexes on that, then actually what we have to do is just go and read everything. Right, because we've got nothing that will help us find them. Right. Okay, so our range search can be a contiguous range search, it can be scattered. If, on the other hand, looking at our customers in London, if we've got nothing, right, we just have to go through from beginning to end. If we've got a secondary index, what we can do is go and do our range search on the secondary index and then go and just pull the records out that we want. Okay, for our customers based in London. Okay. So, what affects us? So let's start thinking about different sorts of ways we can organise a file. So the simplest way, the way we're all familiar with, is a heap file. Okay? When you say in your program or whatever, Notepad, word processor, whatever, to open a new file, then that's basically what you're getting, a heap file. Stuff is put in, and you just keep on putting it in. If you run out of space, you say, operating system, please can I have some more space, and you keep putting stuff in. Right. So there's no organisation except the order in which things are written to the file, which as far as we're concerned is some arbitrary, random, completely unhelpful order. So if we want a file like this, in order to find something in it, on average we have to search half the file to find one thing, knowing that it's unique. Some days we get lucky, other days we're unlucky. So on average, half. If we've got a range search, we know there's more than one thing we're going to retrieve. We've got no idea where they are, so the only thing we can do is to read from beginning to end. Right. Okay, so let's do some quick sums. If we say we've got 1 million records, each 1,000 bytes, and we can get 4 records on a 4,000 byte page, so that means our file has got 250,000 pages. Now, if we're going to find a single record, on average, we will search half the file. Well, let's say that on a current So PC type disk, to retrieve a page from disk takes about 10 milliseconds. Right, so 250,000 times 10 milliseconds, on average half, so therefore we come out to about 21 minutes. Not great.
Surely with solid state disk, this doesn't have an access time.
You're still coming through a disk controller. Your read performance is still it's still measured in milliseconds. Okay. If you like, you knocked a zero off it. Okay. Yeah. So flash memory where you're still talking rather slower than. Yeah.
But you can get about 8,000 IOS on these SSDs.
Yeah, but yeah, I know. But what? All right. So, okay. Let's if you're Facebook, right? 2 years ago, Facebook I think had. Well, I'll remember the correct figure next week. But if I said it has something like 10,000 Postgres databases sitting on servers. Okay, so one of those things that they're talking about disks, and also your solid state memory is still quite a lot more expensive. Obviously tablets and so on, and Apple with AirBooks, kit like that, is driving the price down, but it's still quite a lot more than spinning disk. Yeah, okay. You say price per terabyte.
Yeah.
Okay, so yeah, I agree it's getting better, but databases are getting bigger. Okay, so the point is, even if we're quibbling about numbers, right? You can divide that by 10, right? It's still a long time. And that's how you can find things. And a database of 1 million records in modern terms isn't that big. Okay? Yeah. Databases are measured again. Yeah. Think Facebook, think Amazon, think whatever. Amazon, if you think about it, you see perhaps less than you used to, but Amazon sales ranked 948,537 or something. You think, well, hang on, that means there's at least 1 million items in there, and so on. So, okay, so look, our range search will be twice as long as whatever that long time is. Right. We have to do better. This is unacceptable. Right? You think every time you go to a cash machine, what's happening? How many customers has your bank got? Again, it's going to be several million. Every time you stuff that card in the machine, it goes and talks to the database sitting in the middle of the bank and says, "We're going to let this person take any money out?" And it doesn't take a long time. You do not wait minutes. Again, Visa, somebody I'm sure will tell me that I'm wrong, but Visa on a Saturday afternoon before Christmas, it reckons that it's doing, I think, something in the order of 100,000 transactions a minute. It's that, we're talking big numbers. So, we can't afford to have really slow searches. We do better. Okay. Now, heap files do have their uses, but we'll come to the specialised uses in a minute. We have 3 other sorts which are of interest to us. We have hash files, ISOM files, and B trees. ISOM files are both index methods. ISOM and B tree are both index methods. B tree has got quite a lot of advantages, and actually every time you open up a Postgres database or a MySQL database and say, create a table, what you're getting is a B-tree file. Okay, B-tree works because it doesn't have to be periodically reorganized. ISAM needs manual intervention. So, and then you've got the specialist stuff. We will not talk about those except to say there are many other sorts of index designed for specialized uses. So, coming back to our heap file, what's it good for? What does it do? So the records are placed in the order, you add new pages to the end of the file, and we search by reading from the start. There's no additional structures, no overheads. So actually there are things like logs in particular where they're useful. Now, okay, so if we're inserting into a heap file, it's efficient. We don't have to update anything else. We just have to write to the end of the file every time, one operation. If we know that any selections we do are going to be every page, again, it doesn't matter. We might as well use a heap file because there's no overheads. Most database work doesn't involve reading everything. So, again, specialized things, yes, no. Now, if we want to do operational or specific records, our heap file is inefficient, as we saw from the example. So what's it good for? If you've got very small tables, typically little tables of lookup values, you know, the codes for departments or something where they don't change very often, they're really small, and you can think that they will fit on a single page. If they fit on a single page, then they get read, they get stuffed into the buffer, and they just stay there, stay there, stay there. If they have to be read, it's just one read. Okay? So that's the very small tables. Good. And the main use for history tables or logs of various sorts. So if you've got a database in an industry where records have to be accurate records and every change has to be kept, then what you want is a history file which you hope you never have to use, but the day you have to use it, you'll take quite a big hit because it's going to be important. So you just go right, and okay, so I will use my favourite calibration firm again. They are required by the terms of their accreditation to maintain accurate records of everything they've done for 6 years. So what that means is that their database system has got a bunch of triggers on, and every time anybody makes a change to one of the key tables, that change is stuffed into the history file with a timestamp and a user ID. So if there's any some bit of kit in the North Sea goes bang, some big inquiry, or was it your temperature sensor that was wrong? Who did what to it when? That information is there. At that stage, if it takes you a couple of days to process the history file, nobody would care. It takes a few hours, whatever. So, that's what heap files are good for. Hash files. Okay. Hash files are actually much more interesting. Okay, so each record in a hash file has got a key, and that's the value that's used for searching. So if you've got queries that search by username or customer ID or whatever, especially when you've got unique things, then a hash file is really good. So what happens, we calculate a hash on the key, the thing we're going to search with, and that generates an address, which, because of the history of hashing, is known as a bucket address. A bucket in this case being a collection of a group of pages. Okay, so we then say, All right, we take our hash function, we hash the record, we put it in the right place, and when we come to search, we take our search key and we do the hash, and that generates a bucket address again, and we go to that bucket and just search that little group of records for the one we want. If we're lucky, here we go. Right, so here's an example. Right, so there's our record, there's a hash function. It says, all right, it generates that, puts it there in that bucket, right? And, hello? Right. Yeah, okay, that's fine. We'll come back to the example in a minute. Okay, so there's, we can hash on anything we like, really. But it wants to be something we look at. Now, we keep adding records to our buckets until we get unlucky, our bucket gets full, in which case we have to create an overflow. And what we do, at the end of that bucket, that group of pages, we put a pointer in to where the overflow is. And if we haven't got a very good hash function, we'll get uneven distributions. We won't get an even distribution of records over our buckets, so we have to manage collisions and so on. Okay, there are better hash algorithms to do this, but they're not all perfect. So what happens, here we go, here's our record, we hash it, it goes into there again. Oh dear, that bucket's full, we create an overflow. Right? So when we retrieve it, we hash our key, we get there, we say, oh look, we search that, it's not there. Oh, please can we do an I/O and go and fetch this bucket, and if that bucket gets full, and so on. So if you get a badly designed hash algorithm, you get lots of chaining. That becomes very efficient. If you've got a good hash algorithm, you'll get a very even distribution of keys, you'll get much less overflow, and it'll be nice and efficient. So that's what's tricky about hashing. Right. So it's good for single records, because if we can hash correctly, then we ought to be able to go straight to the page we want. But it's no good at all for retrieving groups of records, because similar key values are not kept together. Obviously, identical key values should all hash the same thing. But if you want to search, do a partial match, say you've got the Smiths, you want the Smiths and the Smythes and all the other variants, then they're similar key values, but they're not the same. So then you have a problem. So that's single records is what hashes are really good for. Right. Okay. Because of the overflow issues, we try and keep space utilisation between 50 and 80%. If we're using less than half the bucket, then it's probably a waste of space. If we're using more than 80%, then we're likely to have too many overflows. So this is, if you've got a hash file and you're using it in a fairly dynamic environment, your database administrator Piero has to look at it and examine the statistics about how full the thing is, reorganise it if necessary. Okay. So if our hash file grows, yes, we're either going to reorganise or use some dynamic hashing method, which is extensible hashing, linear hashing, whatever. I think at the end I've got a couple of references to hashing algorithms for anybody who gets excited by such things. But essentially, hashing has got limited uses, and it's good for that. Now, most of the action happens with indexes. So if you like, heaps and hash files are good special purpose or specialist purpose file types which have particular uses. If in doubt, an indexed file type will never be that far wrong. So, an index, a data structure to provide rapid access to records. Now, we've got the notion here of an index key. Indexes are organised in terms of index keys. The index key may or may not be the primary key. So if you think of your big customer database, your primary key is likely to be the customer number, customer identifier, because you know it's unique, you know it's never null, and all the rest of it. But actually, when people ring up, they don't say, yes, I'm inquiring about customer, you think what your average electricity company customer number is, it's some sort of 40 mixed characters and digits and a few slashes and spaces and what have you in it. You don't quote that unless you absolutely have to. You don't expect to know it. What you say is, yes, I am Smith, I live number 5, and postcode, and they say, oh yes, here you are. That's you, and they can find you. So what you're doing there is your search key is going to be some combination of surname, address, surname, postcode. Surname and postcode would be the typical one. That's the index key. That's the thing that your application is searching on. The primary key is the logical thing which determines integrity, helps you maintain integrity. So here we are. There's our index key. An index key can be a composite of several attributes, whatever. Okay. And very often we're doing partial searches on index keys as well. So we've got a key value and a pointer to a page in our index. We sort our index on the key value, so the index is shorter. Index records are shorter, so you get more of them on a page. They're shorter, makes them easier to search. Means they're quicker to search. So that's good. So rather than searching big long records, we're searching nice short indexes. And the index gives us a page address, which is basically a pointer. It's a pointer which we give to our buffer manager and say, I want that one. And the buffer manager then goes and does stuff. So, what sorts of index can we have? We have the primary index. Okay? So the key, the primary index, is the thing we use to organise the indexed file. So if we have our electricity company customer table, then how might we want to organise it? What are we going to try and retrieve most often? Most of the time, we want stuff out of that because we're coming in on some combination of customer name and address. When we want to do bills, we know we're going to go through everything. So we don't need to organise for billing, because billing just has to read every record. We may have other applications that come in using customer identifier, in which case we might want to have another index, but this won't be the index we'll still organise the file. We might have a secondary index on customer number, even though it's the primary key. And so I'm just trying to get you to separate the notion of primary key and index key. Now, so our primary index has a key to organise it and some organisation used to store the file. Okay, so that organisation is a disk-based data structure. And what we're trying to do is given some query mix, we are trying to minimise the number of disk accesses. All right, because despite the quibbles, what we know is that disk accesses are the thing that are really expensive. Okay? We measure disk accesses in milliseconds, we measure in-memory access in nanoseconds. Now you can quibble about some numbers there, but So, if we can minimise the number of disk accesses, we will get good performance. Right. So, our secondary index is a separate file, right, and it contains index keys for the secondary index, and for each record, a pointer to the page where that is. Okay, so if we've organised our file in terms of name and address, we might well have a secondary index on customer number, which will have one entry for each customer. The key will be the customer number, and you'll get a pointer to the page in there where the thing lives. So again, that would be quite efficient. Right, okay, so it speeds access of certain common queries, and it uses an organisation suitable to the queries it helps. So it might be that your customer number, secondary index, is best organised as a hash file. Yes, because when you want a customer number, you never want a range of them, or at least not unless it's contained a lot more semantics. But your typical customer number, you've got one, I want that one, and only one. If you want a group, you're doing it some other way. What are we doing? Okay. So, right. So I think, okay, so that we've talked about that already. We've talked about that, so we've covered that. It's just a restatement of what I've been talking about. And, right, so that secondary index example I just gave you, we call a dense index because each index entry points to a record. Okay, so one index entry, one record, one index entry, one record. Okay, so there's our index keys, right, and there's our page addresses down there. Right. Now, if we are building an index onto our primary index, our file, then what we want to be doing is just to have a pointer for each page. Okay, so we know that right, if we're 10 or above, unless, so okay, so we're trying to find something, we come in, we start reading, we know we're more than 10, we're less than 30, all right, so that's where we want to go. We're between 30 and 50 and so on. Okay, so that makes that smaller, right, so that same size, if you like, same size, there we are. All right, so we've got the same amount of index space, and we've got up to 120, and by using sparse index, just on this trigger example, we've got rather more. So you can see that if you've got a sparse index, where each entry just points to a page, your index becomes smaller, it becomes easier to search, quicker to search. Right. Okay, so the other term for a primary index is a clustered index. And yeah, we know that. Okay. Now the index for the primary index, or cluster index, is sparse because all our records with the same key are stored together. Okay, so I can actually come back. There we are. So we know that the thing is organised in key order. So all we need to do is to have enough pointers over here to work out which bit to go to, which page to go to. So, yeah. Happy with this? Not terribly by the look of it. Okay. Right. Right. So if you think what you've got here is a file in some sorted order. Yeah. And your index into that file wants to give you a pointer to a chunk of that file. Right, we'll call these chunks pages. Okay, so page, 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 page. So our first index entry gives us an entry into the first page. And anything on that page we can see. Because if we just read the second value, we know whether the target value is in that range. If our target value is in that range, off we go. If it's not, we keep going down. Is that? It needs a little thinking about, and it helps when you actually work some examples yourself. But that's for next week. Okay, so, right, we've looked at that, we've looked at, right. Okay, so here, what do we do when we've got duplicate keys? Okay, because we can have duplicate keys because this is just stuff we're searching for, right? We're searching on name, just think of all the Smiths in the world, or at least in the UK. And there's lots. So, how do we do it? So, the dense index for duplicate keys, it works okay, works fine. You can do some optimizations. You could implement it with single entry per key value and a list of pages or a range of pages that you're looking at. Okay. So if you do a single key entry per key value, you might well put a second page in there, the start page and the end page, something like that. Okay. Now, secondary index with duplicate keys gets more interesting. Right. Because it's a dense index, so we know we've got one of each, and we just have to point all over the place. Right. But again, we search down here, and we know we're going to find all of them. Okay, so we're looking for all the values 10. We know we're going to come down here, and the next one across there, and the next one down there. So you're jumping around all over the place. But if this is quite big, you're saying retrieving 3 values out of 1 million, that jumping around is fine. If you've got loads and loads of these, so that on average you've got one on every page, then you might as well forget the index and just scan the whole thing from beginning to end. Okay, so sparse index with duplicate keys. Right. Okay, we have to watch this one because of things being all over the place. But what you can see, I think, is that by using appropriate indexes, we can, instead of having to search large numbers of things, just search little bits of things. Right, so that's the principal index. Now, we'll talk about ISAM files a bit, and then we'll talk about B trees, and we're just about on time. Good. So, ISAM's the oldest sort of indexed file, developed by IBM in about 1960-something, a long time ago, but it's endured well. So the idea is that records are sorted in key order. We allocate a certain number of records to each page. We leave some free space because we know that we might come back and add some more to it. Now, when we run out of space on a page, we create an overflow page, and it's exactly like we had with the hash files. If we don't do something about it, we'll get lots of overflow pages, so we'll get lots of chaining, and every time we start chaining, then our performance is just going to go really rapidly downhill, because we're going somewhere, we're doing an I/O, we're looking, we're saying, oh, it's not there, please can I have the next one, please can I have the next one, whereas if it were properly organised, we'd go there, we'd just say, yep, that's the one, there it is, everything we want. So, ISAM has to have periodic reorganisation. This reorganisation has to be done by a person. Now, that's not actually very good, because you think of all the contexts in which database management systems get used. Think every little business, pretty much, with an IT strategy worthy of the name, has got database management systems to use there. Again, if you're Facebook and you've got 10,000 servers, then you really want to be looking to see, oh, that one's overflowed a bit. We ought to do reorganisation on it. Take it down. And to do that reorganisation, you sacrifice availability and so on. That's your problem with ISAM. So we'll have a look and see what the organisation is. Okay, so here's our ISAM. Now there's our index file. Here's the index. So right, so we're trying to insert records 25 and 35. So we come, it's more than 10, it's less than, oh yeah, okay, so off we go onto this page, we put our 35 in. Great, we've won. That's fine. Right. Now we do 25, 10, okay, so, right. So we've got to put it on here. Oh dear, there's no room. So we create an overflow page and put it in there. Right. So when we try and retrieve it, we have to do 2 IOs instead of 1. Okay. There we are. So it's all linked together. You can see how that works. Right. Now, obviously, so far I've just shown you one level of index. We're talking about things with millions of records in, therefore we can generalise this. We can say, oh look, we've got an index into a pile of things. We can have another layer of index into our index, and we can have an index into the index into the index, so at each stage we're just finding the thing we want. Okay, so we're not having to scan units. Because if you think, oh, we're going to scan a scan of a Facebook user, you're on a one-level index, you're going to be there for quite a while. So what you want is to be able to travel down an index. So the upper levels of the index are always sparse. With fewer pages, they're easier to sort and so on. And we normally create any index structure with an initial fill of about 70%. So we'll leave about a third of it free so that we don't have to reorganise immediately. That applies to ISAM and B trees. Okay, so ISAM is simple. We can do easy scans because the file's sequential. It's a static structure, so we're either going to get chaining or reorganisations. We can do better. We can do better, and the better is called a B tree. And you know about B trees because every time you use Postgres, you go and create it. So that's pretty much what every DBMS does by default. Now, okay, a B tree is a multi-level dense index. So it's got a single root node, it's got internal nodes which contain pointers and key value pairs, and then it's got leaf nodes which either contain the records or which point at records in another file. Okay? So it is a balanced tree, and it keeps itself balanced by splitting or combining as inserts and deletes happen. Okay, so if you've put too many records into a B tree node, it will say, oh dear, I'm getting full, I'll split. And it splits, and off it goes again. If you keep deleting records, it will say, oh, I've got nothing left, so I'll do a combination and I'll shrink. So it's a self-maintaining index structure in that sense. Right. Okay, so a very simple B tree example. There's our root node. We know that roots always appear at the top because we're computing people, and there's only one of them. So, okay, so we've got a root node, we've got a couple of intermediate nodes, and we've got some leaf nodes. Right, so what we're saying is Okay. If we come in here with a value, right, so we say, oh, our value is greater than 100, off we come down here, and we can see we've got some values there. We're looking for 156. Yep, there we are. There's our minimum value there. So it's 100, between 150 and 180. Off we come down to this page, and there we are. And we can go and get the record we want. So what have we done? We've done 1, 2, 3, and off we've got. So this is pretty efficient. Okay. So I'm showing, because this is a lecture, I'm showing a B-tree node with 3 entries. In practice, you would expect to find several tens or several hundreds in a B-tree node. Okay, so B trees are very bushy. They don't grow up very quickly, but they go out. Again, which makes them efficient. So, in terms of database design, when you're thinking about things like how long should your character fields be, I don't know, not sure how long this is going to be. I know what, I'll make it a varchar 1000. The fact that it's normally only, it's about 80 or something, you think, well, that's all right, plenty of space. Then you find that's actually your major search key, and what you're doing is storing an extra 900 bytes of nothingness in your index nodes. Not such a good idea. So when you're thinking about things which are being searched on, you want a pretty good mapping between maximum size and appropriate data type. You want to be using everything you can, because you don't want to be storing rubbish space in the index. It costs you. Okay, so what have we got? That's our simple example. Right. So when our file is created, we again, similar to ISAM, we start with a fill factor of about 70%, and if we're being clever, if we're sort of sitting in the bowels of a Viva or some equivalent, we know that our sort of difference between 70% and 80% full probably means 3 or 4 large disk arrays. At that stage you think, yeah, okay, well, if we don't think insertions are going to be frequent, if we know they're not going to be frequent, then we can afford to have less free space. Again, that will help our search because our data is occupying fewer pages. But if we know that insertions are going to be common, so if we're, on the other hand, sitting in the middle of a bank, looking at how much space should we leave to record transactions on people's current accounts, we know that we're going to get lots of these things. We're going to have lots of insertions, so therefore we want a lot of free space. Okay, and if we know that we've got some key sequence, so typically something which involves date stamps, or customer orders or order numbers or something, which always increase at the end of the sequence, then we need more space. Because what we're doing, we're putting all our insertions in at one end. So we're always trying to unbalance our tree, which means it's going to want to reorganize itself more because we're trying to make it unbalanced, and it says, no, it's got to be balanced. Okay. Right. Okay. So, if we're looking at any internal root node in a B tree, what we can see is, so in this little example, we've got our first value is 120, and that says that is the maximum key value in that branch of the tree. Okay, 150 maximum key value in the next, 180 maximum key value in the next, and so on. Okay, so you can do you're doing quite a lot with some quite small structures there. And then our leaf node, okay, so it says that's some sort of pointer to something with some key of 150, 156, 169, and then at the end of each leaf node, you put a pointer in to the next leaf. So that when you come along wanting to do your range search, so if we, let's come back here. Okay, so if we want to do a range search, we want everything between 100 and 180. Then we want to come down here. We start reading along. We don't want to have to go back up there to come back there. We want to come along, whoop, hop, top, 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 hop. So if we just put a pointer at the end there, it means we can go along until we get to the end of our range, rather than have to go back up the index each time. Right, now, sooner or later in our B tree, the page gets full. And, oh dear, it has to split when it's, okay, and if it's got too few, it will get merged. So, right, so what the moment it gets less than half full, it'll get merged, if it can. Right, okay, so in this case, let's look at what happens with insertion. Okay, so we're inserting key 32, so off we go. We know it's less than 100, off we go. It's more than thirds, so off we go. There we are, it fits. Great. Right. Now, okay, so slightly different structure. We're inserting 7 this time. Off we go. Look, 7. Right, so insert it there, and we create a new page, and we're picking up things, so we're balancing the tree. Okay, so what we've done, we've reorganised the chunk of the tree so it's nice and balanced to have the appropriate number of keys on the new page. Right, because we would have overflowed, so we create a new page and off we go. Yeah, is that happy? Yeah. Okay, right. Now, things can get horrid. Okay, so we're putting in 160 in this case. We come down, we can't do it, so we come down initially 150, and we are full. So at the stage we're full, we actually reorganise things, and we create a new page. That causes a split, and it will split all the way back up. Okay, because we create a new page there, we can't get it in there, off it goes. Now, what that means is that occasionally B trees will really badly misbehave and will have a wait while it reorganises itself. These occasions are pretty rare. This is the good news. So that actually, the reason B trees work well is because in practice, the number of times this sort of big reorganisation happens is very few. Therefore, for most things, it works well without manual intervention. Right. Okay, so a B tree is good for exact and part matching on an index key. It's good for range. Okay, so you can see how with that tree structure matching on the keys works well. We can see, because we've got the pointers along the bottom, that our range searches are going to work well, and we can see that we can handle inserts and deletions pretty gracefully. We don't get stuck with huge performance hits every time. Once in a long time, we'll have a query, an insert or a delete, that causes a performance glitch, but that's once in a long time. That's the price we can pay. Therefore, we use it as the default, because it's again, you think most people put database servers in, DBMSs in, and expect them just to work decently. And this is why they work decently, because by default, Unless you tell it something else, a DBMS will give you a B tree organised or indexed on primary key. This may not be what you actually need, but if you have to pick something for a default, that's about the best you can do.